The Feynman Lectures on Physics. This lecture, Conservation of Energy, was presented by Dr. Richard Feynman on October 6, 1961, at the California Institute of Technology.
There will be no summary of the previous lecture. There's no summary of the previous lecture, just to remember whatever you can remember from it. No vital points. The next two lectures after today will be given by Professor Matt Sands, because I'm going to a meeting in Brussels. And I'll come back next Tuesday, the Tuesday following. Today's lecture is on one of the laws of physics, and beginning, of course, the detail looking at the different aspects of physics. We just finished our description of things in general, and now we look more specifically in particular what a law of physics looks like. And so I picked one out to illustrate the ideas and the kind of reasoning that might be used in, say, theoretical physics. So the lecture today is on the conservation of energy. There is a fact, or if you want to call it a law, governing all natural phenomena that's known to date. There's no exception known to this. It's exact as far as we know. And the law is called the conservation of energy. It states there is a certain quantity, which we call energy, that doesn't change in the manifold changes which nature undergoes. Now that's a very abstract idea, because it's a mathematical principle. It says that there's a numerical quantity that doesn't change when something happens. It's not a description of a mechanism or anything. It's just a strange fact that you can calculate some number, and when you're all finished watching nature go through her tricks, you calculate the number again, and it's the same. Something like the bishop is on the red square now, and after a number of moves, details unknown, it's still on some red square. It's a law of this nature. Since it's an abstract idea, I would like to illustrate the meaning of it with a rather silly example, but it does illustrate the idea. I want you to imagine a child, perhaps Dennis the Menace, who has blocks. But you must appreciate that these blocks are absolutely indestructible and cannot be divided in pieces. They're just, each is the same as the other. And we'll suppose that he has, say, 28 blocks. Now this child is put into a room by his mother in the beginning of the day with his 28 blocks. And at the end of the day, I don't know why she's so curious, but she counts the blocks very carefully and discovers a phenomenal law that no matter what he does with the blocks, there are always 28 blocks. So this goes on for a number of days until one day there are 27 blocks. But a little looking around shows that there's some under the rug. You have to be careful to make sure that you look everywhere in order to make sure that the number of blocks doesn't change. One day, however, the number of blocks appears to change. There are only 26 blocks. Careful investigation indicates that the window is open, and now looking outside, you can find the other 2 blocks. So you bring them back in again, and everything's all right. Another day, careful count indicates the existence of 30 blocks. This causes a considerable consternation until it's realized that Bruce came to visit, and he owned blocks. Yes, perhaps a few. So after we've gotten rid of some of these things, that we close the window, we don't let Bruce in, then we see everything's going along all right until one time when we count there are 25 blocks. But there's a box in the room, the toy box that the boy has, and the mother goes to open the toy box, but the boy says, "No, don't open my toy box," and screams. He doesn't want to know. The mother is not allowed to open the toy box. Being, however, extremely curious and somewhat ingenious, she invents a scheme. She knows that a block weighs 3 ounces, so she weighs the box at a time when she sees 28 blocks. And it weighs 16 ounces, so the next time when she wants to check, she weighs the box again, subtracts 16 ounces, and divides by 3. So she discovers the following. Number of blocks that you can see, if you have to add to this, number of blocks seen, plus weight of box minus 16 ounces divided by 3 ounces, And then it's constant every time, up to a point. There then becomes some gradual deviations. There appear some deviations, but careful study indicates that that dirty water that's in the bathtub is changing its level. In other words, the child is throwing blocks into the water. You can't see it because it's so dirty, but you can find out how many blocks are in the water by adding another term to this formula, which is height of water in tub minus 6 inches divided by a quarter of an inch, because each block that goes in is a quarter of an inch. And so with a gradual increase in the complexity of the world, you find a whole series of terms representing ways of calculating how many blocks are in places where you're not allowed to look. And as a result of this, it's possible to find a complex formula, a quantity, which has to be computed, which always stays the same in this situation. Now, I would now describe the analog of this to the conservation of energy. The most remarkable aspect of it is that I want you to abstract from this picture. First, there are no blocks. You never see the blocks. So you take away that term. Then you discover yourself calculating more or less abstract things. The analog has the following points in it. First, sometimes when you're figuring out the energy, some of it leaves the system and goes away, or sometimes some comes in. So in order to verify the conservation of energy, you've got to be careful that you haven't put any in or taken any out. Second, that energy has a large number of different forms, and there's a formula for every one of the different forms. I've written a number of the forms here. I see I left out elastic energy. And there's a formula for every one of these things, and we find out what the formulas are, and then total them up, they won't change except for going in and out. I'll give you that, well, we can do that down if you want. So that's the relation of the analogy. It is important to realize that in physics today, we do not have any knowledge of what energy is. My analogy is bad because we do not have a picture in physics today that energy comes in little blobs of a definite amount. It does not that way. And it is not the definite blocks, but there are formulas for calculating some numerical quantity. When you add it all together, it gives 28. Always the same. We have no deeper understanding of it than this. And it is an abstract thing. It doesn't tell you the mechanism or the reasons for the various formulas. Now, the conservation of energy can only be understood if we have the formula for all these things. And I could, of course, list the various formulas for different forms of energy. We call these things different forms of energy, different hidden ways of calculating the number of blocks. However, I want to amuse us today by discussing the formula for gravitational energy around on the surface of the Earth here, not going very far away. And this, we call this term, the sum of the weights times the heights, gravitational energy. The energy which an object has because of its relationship in space relative to the Earth. And the formula for gravitational energy, as long as you're not too far from the Earth, the force weakens as you go higher, so this is only a approximate. You might try to find out where the error is in this analysis, if the heights are so high that the force weakens. Gravitational energy has the formula, the sum for all the various particles. We don't have to remember the sum, it's always the sum of all the things that are there, you add it together. Weight times height. And that's an illustration of it. Now the question is, of course, it's a very beautiful set of reasoning. The only thing is, maybe it's not true. After all, nature doesn't have to go along with the reasoning. Perhaps, for instance, perpetual motion is in fact possible. So that some of the assumptions may be wrong, or I may have made a mistake in reasoning. So it's always necessary to check. And it turns out experimentally, in fact, to be true. Incidentally, the general name of energy, which has to do with location relative to something else, is called potential energy. In this particular case, more specifically, I would call it gravitational potential energy, to give you a high-class word. If it's a question of electrical forces against which you're working, instead of gravitational forces, you're lifting charges away from some other charge with a lot of levers, then the energy content is called electrical potential energy. The general principle is that the change in the energy is the force times the distance that it's moved, that your force is pushed, and that's a change in energy in general. But we come back to a lot of these things and make them when we go on with the course, of course. Now this principle, the conservation of energy, is very useful for figuring out what will happen in a number of circumstances. And I'll illustrate some of those. Just because you probably learned an awful lot of laws in high school to figure out what happens under different circumstances, I assure you they're all the same thing. So you didn't have to memorize 75 rules. You could figure it all out. Take the simplest example as an inclined plane. Suppose that we have an inclined plane which is happily on a 3, 4, 5 triangle. And we have here a weight, which we'll call, we say, a 1 pound weight on the inclined plane with a pulley here. And on the other side of the pulley is another weight, X or W, say unknown. We want to know how heavy this has to be to just balance that. Now, how can we figure that out? Well, we say, if it's just balanced, then it's reversible to move up and down. And I can consider the following situation. In the initial circumstance, I suppose that the weight, the 1 pound weight is down here, and that the weight W, say, is at the top, wherever it is, that is, and there's a pulley here, so. And then after, when it's slid down in a reversible way, now, we can move back and forth with its balance. Then we have here the 1 pound weight at the top of the thing, and the weight W is down here, some distance or other from the place it was before. What distance? Oh, the slant distance, 5 feet, or 5, whatever they are, 5. So the weight W is falling 5 while the weight 1 is lifted 5. No. It's the height above the ground, the formula says. How far did we lift the weight? We only lifted the weight 3 feet. So therefore we lifted 1 pound by 3 feet, and we lowered W pounds by 5 feet, and therefore W is 3/5 of a pound. So you see, you can deduce that by very cleverly from the conservation of energy. Cleverness, however, is relative. It can be deduced in a way that's even more brilliant from the conservation of energy by a way invented by Stevinus, and which is on his gravestone, his tombstone. That's his tombstone. And that explains that it has to be 3/5 of a pound. Because it doesn't go around, says he. And it's evident that this part of the chain is balanced. So the pull on these 5 weights here must balance the pull on the 3 weights here into whatever the ratios of these legs are. And it's even true if it's an doubling. And so you see, by looking here, that it's 3/5 of a pound. So this was clever, but that's even more clever. It's 1600. Anyway, if you get an epitaph like that in your gravestone, you're doing fine. Let me illustrate with the more complicated problems that the same thing works, and you don't have to. This is very simple. And let's take one of those wonderful things that they're always annoying you with. Something like this, you see. We'll just make one of these up. I have one made up. I have a screw thread, so a jack, you see, which has a screw thread in it, on it like that, that's in a nut. And then you turn it with a long lever in the nut, in the jack here. And the lever is 20 inches long, say, and you push it around this way. And that there are 10 threads to the inch on the jack. That's an inclined plane, you see, of some kind of complex inclined plane. And I'd like to know how much force do I need here to lift 1 ton here. A ton is 2,000 pounds, say. So let's see. Suppose that I want to lift the ton 1 inch. Then I have to turn this around 10 times. So to lift 2,000 pounds by 1 inch, I have to turn this 10 times around. When it goes around once, It goes 2 pi times 20. It goes around a distance of approximately 125 inches around per turn. So I must really turn 125 inches is the distance that I go. And if I had various pulleys and so on, I would be lifting an unknown force, unknown weight, W, to bounce. And so you find out what W is. It's about 1 pound and 0.6 according to this. Well, it came out 2 pounds last time. Oh, I see, I had 8 threads per inch. That made it easier. But anyway, with 10 threads per inch, it comes out 1.6 pounds for the push. And you see it's by the conservation of energy. Take still another example. We'll take somewhat more complicated one. Consider the complex problems of this dopey nature, which is this. You have a rod, or a bar, which is supported at one end, and it's 8 feet long. And then in the middle of the thing, at 4 feet, somebody has put a weight of 60 pounds. Or, I don't know, there's a bridge and there's a truck on it, huh? And there's another truck, you always make it sound better when you say that. There's another truck of 100 pounds. No, there's no truck of 100 pounds. There's a Morris Mini Minor here at a distance of 2 feet from the fulcrum. We would like to know how hard do we have to pull over here in order to keep all the stuff from falling down, disregarding the weight of the rod. So we say, okay, well, it's sort of this way. Suppose you had a pulley here and you had a weight down here hanging on a pulley. How big would the weight W have to be in order that this thing won't balance? How can I figure that out? Well, I imagine that the weight falls any old distance. I picked it to make it easy for myself. I suppose that the weight went down a short distance, 4 inches. That is, I imagine that this lever would lift itself up around this fulcrum, like the dotted line here, a height here of 4 inches. How high would then the 60-pound weight lift? Well, it's easy to see because it's 4 days up. So it lifts 2 inches here, and this one is a quarter of the way, so this lifts 1 inch here. Therefore, the principle that the sum of the height times the weight doesn't change. The change in this will be 0. In other words, the weight times 4 inches down, if you like to think that way, you can put the equation any way you want, plus 60 pounds times 2 inches up, plus, that's up, 100 pounds times 1 inch has to add up to nothing, you know, if you do it with minus signs. Otherwise, you put ins and outs are equal. It's the same thing. And so you have here 120, 220 divided by 4 is 55. You know, it looks good how fast he does arithmetic, but he's done it before and he checked the number, so I know it's good. So you find you have to have a 55-pound weight there to balance it, and thus you can work out the laws of balance, statics, of complicated bridge arrangements, and so on. This is called the principle of virtual work, because in order to do this argument, we had to imagine virtually in our imagination that it would move a little bit. Even though it's not moving, we use the motion, and we use a very small motion, because if I try to use 400 feet here, it would get a little bit confused by having gone around so many times. So we use a very tiny motion, so it's easy to figure out. The smaller, the more easy it is to figure out. Actually, you see, it goes in a curve, and it isn't exactly 2 inches and so on. But you take an infinitesimal distance, and that's called the principle of virtual work, which is use the principle of conservation of energy to get the laws of those systems of this kind. Now, that's not the only kind of energy, and in order to illustrate a more, another type of energy, we take another form of energy. Consider a pendulum, in which when you drop it down, you let go and it comes back, it lifts itself up, it lowers, and where does the energy go? I took gravitational energy when it's down at the bottom, it hasn't got it anymore. It's lost. But nevertheless, it can climb up again. And the way it climbs up is because the way we must keep track of it is to say, although it's lost from gravitational energy here, it has another form. Evidently, of course, it's in motion. And it's by virtue of its motion that it's able to climb up the height again. So we have the conversion of gravitational energy into some other form when it comes to the bottom. We have to get a formula for the energy of motion. I would like to illustrate, as well as I can, that that a weight by gravity can, even if it does interchange into motion and come back into gravity, cannot in any way increase the height in which the ball is left. In other words, this ball can't possibly come any higher than the point at which it was left. So we have the situation that when the thing has fallen to this distance, it's lost its gravitational energy, and if the law of conservation of energy is right, there must be in some other form, and that form is motion. So we would expect, if the law of conservation of energy is right, that it doesn't make any difference what kind of a way it comes up. And you see, if you can, that even if it comes on a shorter rock, it comes to the same height as if it's left. That is, the motion is converted into the height by the pendulum. And it doesn't make any difference by what machine the motion is converted into the height, or by its reversible. When a pendulum is nearly reversible, there's a little friction up here. So that this will go to the same height. If we had it at a different place here, of course it's a little different, but it comes to the same height here. And the worst the situation is here, what's it going to do if it can't quite make it? So there we are. Now when we see that when at the bottom of the swing it has less gravitational energy, it can still recover. And the energy that it has at the bottom of the swing depends on only the height that it came down, only the height that it has to recover. We illustrated by the pendulum that it doesn't make any difference by what route it recovers the height, it is able to come up to the same height. Therefore, in the motion at the bottom is a quantity of energy which permits it to rise a certain height, and has nothing to do with the machinery by which it comes up or the path by which it comes up. So that we have an equivalence formula, something like that one that we wrote for the child clocks. We have another form to represent the energy. And it's easy to say what it is. The kinetic energy at the bottom is given by the following formula. The kinetic energy at the bottom is the weight times the height that it could go corresponding to that velocity. Well, we just said that. But what we need is the formula that tells you, given this, we want the formula in terms of the velocity. See, every velocity that corresponds to a certain height, by some rule or other that has to do with the motions of objects. If we start something out with a certain velocity, say straight up, it'll reach a certain height. We don't know what that is yet, but it depends on the velocity. There's a formula for that. Then the formula for kinetic energy must be, if you see an object moving with velocity v, calculate the height that it could come to, and multiply by the weight. That'll be correct. Now when we learn about the laws of falling bodies, you probably know that the formula for this, the relation between the velocity and the height, is in fact that the height that it can go is the square of the velocity divided by twice a constant which is called a gravitational constant. So with that formula for the height in terms of the velocity, we can write this thing this way, that the kinetic energy is the weight times the velocity squared over twice the gravitational constant. And so for different speed objects, we can calculate the kinetic energy, the energy of motion. And the energy of motion is nothing but the weight times the height that that motion could lift it to if it was shot straight up. Of course, it hasn't got to do with the fact that you're in a gravitational field that motion has energy. It doesn't make any difference where you got the motion from. That formula for kinetic energy is more general than the particular, but it's a general formula for various velocities. Both of these formulas are approximate. This because it's not right when the heights are wrong, when the heights are so high that the gravity is weakening. This because of the relativistic correction of height speeds. But when you get the exact formula for the energy, then the law of conservation is exact. Well, we can continue this way and illustrate the existence of energy in other forms. One that's not written there is elastic energy. If I pull on this spring, I have to do some work. I could use lift weights with it. Now that I have it down, I can lift weights with it, right? So therefore, in its expanded condition, it has a possibility of doing some work. So if I just added the sums of weights times height, it wouldn't check out. I have to add something else to account for the fact that the spring is under tension. It's in some way. I must add a term, I should add it here, elastic energy, which is the formula for in a spring when it's stretched, how much energy is it? And so here, for instance, if I let go, then the elastic energy is converted as it passes through the middle to kinetic energy and goes back and forth into compressing the spring and elastic energy, and it's reversible back and forth between elastic and vertical motion. But, and this goes on and on. So that there's an exchange there between elastic energy and kinetic energy. There's also some gravitational energy going in and out, but you can do this experiment sideways if you want to. Incidentally, now it's gotten into a peculiar condition. It's not moving up and down. It's in the same position as it was before. Where's the energy that I put in? Now the energy is in rotation when it's turning. But when it's turning all the way, where is it? It's in twisted spring. So we have converted energy from vertical pull of the spring to vertical motion to rotational motion to rotational twist of the spring, and so on back and forth. It keeps going until the losses destroyed. Now come the loss. I keep it all the way through. I'm pulling little weights. I'm telling you the thing goes on forever, but in front of your eyes you see that it's stopping. Where's the energy when it's all finished moving up and down? In other words, I have the sums of the weights and everything else. What happens? What happens in all these circumstances is this, that inside this spring, the things are made out of lots of atoms. And although with great care in the delicacy of the arrangement of the parts, you can make things so that as you roll something on something else, none of the atoms do any jiggling at all. You have to be very careful. Ordinarily when you roll, because of the irregularities of the material, there's bumping and jiggling and the atoms start to wiggle inside. So we lose track of that energy. We find the atoms are wiggling inside here now, after this is slowed down, they're jiggling in there in a random and confused manner. There's still kinetic energy, all right. There's kinetic energy, but it's not of the object. What a dream, huh? How do you know there's any kinetic energy? It turns out that with thermometers and so forth, you can find out that in fact it's warmer, and that there really is a development of kinetic energy by a definite amount. And this form of energy we call heat energy, but we already know that this is not a new form. This is just kinetic energy, an internal motion. And one of the troubles with all these experiments that we do with matter on a large scale is that we can't really demonstrate the conservation of energy. We can't really make our reversible machine, because every time we move a large clump of stuff, the atoms do not remain absolutely undisturbed, and so a certain amount of random motion goes into the atomic system inside. And we can't see that, but we could measure that with thermometers and so forth in the form of heat energy. There are lots of other forms of energy, and of course I can't describe them any more in detail. There's electrical energy that has to do with pulling and pushing by electric charges. There's radiant energy, the energy of light, which we know is a form of electrical energy because light can be represented as wigglings of the electromagnetic field. So this thing is equivalent to this. This one is equivalent to this. There's chemical energy, the energy which you call the energy which is released in the chemical reaction. Actually, elastic energy is to a certain extent something like chemical energy, because chemical energy is the energy of attraction of the atoms one for the other. And so is the elastic energy. So both the elastic energy and the chemical energy are forces of the atom. Why do I cross them out? Because our modern understanding of these is the following, that this chemical energy has two parts. Kinetic energy of the electrons inside the atom, so part of it is kinetic, and electrical energy of interaction of the electrons and the protons, and the rest of it, therefore, is electrical. So with electrical and kinetic, we have an understanding of these other forms. Next, we come to nuclear energy, the energy which is involved in the arrangement of the atoms, the particles inside the nucleus, and we have formulas for that, but we do not have the fundamental laws. We know that it's not electrical, and it's not gravitational, and it's not purely kinetic. So we don't know what it is, so there's an additional form of energy here. Finally, associated with the relativity theory, there's a modification of the laws of kinetic energy, or however you want to call it, so that this is combined with another thing called mass energy. It turns out that an object has energy from its sheer existence. If I have a positron and an electron that are standing still and are doing nothing, never mind gravity, never mind anything, they come together, disappear, energy, radiant energy will be liberated in a definite amount. And the amount can be calculated from only knowing the mass of the object. It doesn't depend on what it is. We make these two things disappear and we get a certain amount of energy. When a mass is m, mass is weight divided by g, by the way, so if you like, this is mass times velocity squared over 2.
This is the way to remember it. It's much better because it has nothing to do with the gravity that way. And the formula here is mass times the speed of light squared is the energy associated with the mass. Finally, let me remark on the question, where can we get energy? Our supplies of energy today are all from the sun, rain, coal, uranium, and hydrogen. The sun makes the rain, of course, and the coal also, so that both of all those are from the sun. Although energy is conserved, nature doesn't seem to be interested in it. She liberates an awful lot of energy from the sun, but only 1 part in 2 billion falls on the earth. So that nature has conservation of energy, but doesn't really care. She spends a lot of it in all directions. In the future, we expect to get energy. We have already got energy from uranium. We can also get energy from hydrogen, but it's now only an explosive and dangerous condition. If it can be controlled in thermonuclear reaction, then it turns out that the energy could be obtained from a quart of water a second is equal to all the electrical power generated in the United States. So with a faucet running 15 gallons of water a minute, you have the fuel to supply all the energy in the United States that's used today. Therefore, it's up to the physicists to figure out how to liberate us from the need for having energy. And it can be done in practice. Thank you.